Hello, my name is Zoe Turner, and this is my Lab 2 magnetic field of permanent dipole magnets. The purpose and goals are to investigate the distance dependence of magnetic field of a small magnetic bar, simulate the magnetic field using glow script, and compare the measured magnetic fields to the simulated one. Our findings were the net distance field increased as the distance shortened, and then the magnetic dipole moment was 1.5 a to the m squared. The measured off-axis of the magnetic field was about 1.5 10 to negative 5 teslas, and the simulated off-axis was about 2.9 10 to the negative 5 teslas. Some key concepts we need for this lab is Biot-Savart's law, and this is the magnetic field produced by an object at an observation point, the derivative of the magnetic field dB, the B loop, the magnetic dipole moment, which is equivalent to I times the loop area, which is I pi r squared, and the direction of the on-axis magnetic field is the same direction as the magnetic dipole moment. The experiment for our system, we have our magnometer, and surroundings is the bar magnet, and the bar magnet was treated as the magnetic field. The materials we need is meter sticks, tape, magnometer, bar magnet, and the magnometer is oriented on the x-axis, which had it as 0. Measuring on axis, we measured the distance between the magnet and the magnometer, and measuring off axis, you recorded the y direction of the Earth's magnetic field and applied it to the magnometer and the distance. What was observed was as the magnometer moved closer to the magnet, the measure of the x component of the magnetic field increased. Here's my experiment and data. Some errors that might have happened was the magnet wasn't strong enough. My location definitely had an effect on my data, and the data from my phone wasn't accurate. Some results were the equivalence of the regression line from the data was the slope of the regression line equals n and the y-intercept equals ln k. We use these constants to set up and solve the magnetic dipole moment. And then we subtract the Earth's magnetic field from the y direction. So here's some of my code. As you can see in the picture of my chart or graph of where all of the magnetic fields are, you can tell where the positive end of the magnet is and where the rest of the magnetic field is pointing to. So some what ifs. What if the experiment we oriented our setup so to compensate for the magnetic north? What if we haven't done that and instead we just laid our meter sticks into some angle respect to Earth's magnetic field? What would have changed was our outcome number. I don't think our actual magnetic field would change, but we would have to compensate for Earth's gravity at x and the y-axis. So what if we had two identical magnets, and what if we redid the experiment, but instead of using a single magnet, we used two identical magnets stuck to each end? How would our measurements differ? I feel our magnetic field would be a lot stronger because from doing past practice tests and just working on homework questions, when the magnet was either 2 times as strong or even 1.5 as strong, that drastically changed the magnetic field. So it made it either that 1 times as strong or twice as strong, or if there was less magnetic field or less magnets, then the charge would be either a half or a fourth of what the original charge was. So in conclusion, the closer the distance is to the closer the distance, the stronger our magnetic field. And at 20 t, the distance, or 20 teslas, the distance was about 2 e to the negative 1 meters. And about 70 teslas, the distance was 1.4 e to negative 1 meters, which is showing that the stronger it is, the closer it is. The magnetic dipole moment was about 1.5 amps and meters squared, and the magnitude of off-axis was 7.5 e to the negative 5 teslas. And the magnitude we simulated was about 2.9 e to the negative 5 teslas. And reiterating the errors, the data, from my phone wasn't accurate, the magnet wasn't super strong, and other magnetic fields were also into play, like phones, TVs, microwaves, and more.